Okay, so can you hear me? Yeah. So in these lectures, I wanted to talk a bit about the similarities and differences between the calculations we do in de Sitter space and calculations we do in anti-de Sitter space. And I will try to rephrase. I'll try to point out what things are similar, what things are different. And I will start by reviewing the way we do computations of physics in de Sitter space, how we compute expectation values. And then we'll go on onto anti-de Sitter space, and then we'll go back to de Sitter space and try to see what differences and similarities we have between the two calculations. So the first topic I'll discuss is the calculation of is how to treat quantum fields in de Sitter space. So Lenny briefly mentioned the fact that an observer sees temperature in de Sitter space, and that was something that was discovered in the 70s when people put quantum fields in de Sitter space and analyzed the physics of such quantum fields. And this is a calculation that you should really, I think you should do this calculation yourselves. You should understand all the 2's and pi's to make sure you understand how it's done. I think it's a calculation. This will be central to many of the things that will be discussed later. And you should really, it's one of these calculations that they should be able to wake you up at the middle of the night, and you should be able to do it, and in any coordinate system. Okay. Once it happened to me. Once I was woken up in the middle of the night, and I was lecturing at England, and it was the middle of the morning for them. It was middle of the night for me. But I overslept, and they came, knocked at my door. You should lecture. And it wasn't exactly this calculation, but if this happens to you, you should be able to do it. OK. So we are going to consider a quantum field with an action grad phi squared. It could be massive or not massive. I'll discuss first the massless case and point out the differences with the massive case. So this is an action for the field in de Sitter space. And let's consider de Sitter space in the flat slicing. So this is now the metric. And so we'll use these conformal time coordinates. So as Lenny talked about last lecture, eta is what he called t. Sorry for the change of notation, but if I call it t, I'm going to mess it up. And x are the spatial slices. So these are 3 coordinates of R3. And then we have conformal time. Conformal time runs from minus infinity to 0. So this is eta. Eta equal to 0 is the infinite future of de Sitter space. Eta equal to minus infinity is the infinite past. Okay. Now, if we follow 2 observers who are at constant x, such observers are geodesic observers. So we could take an observer at constant x. He will remain at constant x. It's not subject to any force. It's an observer just freely floating in de Sitter space. We take 2 such observers, and their proper distance is growing. So it's growing like 1 over eta squared, right? This is just telling us that their distance is growing. And as Lenny mentioned, there is a particle horizon for each of them. And so so at very early times, they could be in causal contact. This observer can send a message to this one here. But after this slice, this observer cannot send any signal to this observer anymore. Okay. Now, in order to do this calculation, it's useful to break up the field into Fourier modes. I mean, we can use the symmetries of de Sitter space to our advantage. And we have a translation symmetry in X. So we're going to expand the field phi in Fourier mode. So we use the usual Fourier decomposition, phi of x. And now each of the modes depends only on eta. Okay? And now we put it back into the action, and we see that we have an action for each Fourier mode. We have an action which depends only on time. And So with this metric, the action has the following form. Okay, this is just the gradient of the field. That's what you would have in flat space. Okay, and then there is the factor of 1 over eta squared. So there is a square root of g. So in that, I mean, this comes from the square root of g and an inverse g alpha beta, right? This would have a 1 over eta to the fourth. This has an eta squared. We got this factor of eta. Okay, that's how this comes about. And now we should look at this action, and we see the ever-present harmonic oscillator. So any problem that usually has a solution is a harmonic oscillator. So we see a harmonic oscillator with, you can think of it as a time-dependent mass. The frequency is k squared. So it's a harmonic oscillator with a time-dependent mass, or equivalently, you can think of a harmonic oscillator with an h bar where h bar depends on time, and so h bar is very large at early times and very small at late times. Similarly, we could say that the mass, so the mass of the harmonic oscillator, which is what sits here in front, goes to infinity at late times when eta goes to 0, and goes to 0 at early times. Hard to read? Okay. This part here is hard to read? Okay, let me just say it. But then you'll say it's hard to understand me. Yeah, I understand. Okay. Yeah, so the mass goes to infinity when eta goes to 0, so late times, and the mass goes to 0 at early times. Now, the mass going to infinity means the harmonic oscillator is becoming very classical at late times, and that we'll see more clearly later. Okay, so we need to quantize this. Well, we have phi, we have its canonically conjugate momentum, pi, which is the derivative of the Lagrangian with respect to the time derivative of phi. And this is just nothing else than. And then we should impose the canonical commutation relations and so on. Now, in systems like this that are exactly solvable, one can find operators which are time dependent. And we do this by taking the field phi is an operator, and expressing it as a linear combination of two operators with some coefficients which are solutions of the classical equations of motion for phi. And if we do this, we make sure that these operators A, that appear A and A dagger, that appear here, are time independent. Now, we can do this in many possible ways. F is a classical solution of the equations of motion of this Lagrangian. Now, we can do it in such a way that the commutation relations between A and A dagger are the ones that we are used to for the case of creation and annihilation operators. And this can be, I mean, you can set that if you find some solutions F and F star, you can set the normalization of the solutions by imposing this condition together with the condition that pi with phi is the usual I. Okay. So imposing the usual canonical commutation relations between the phi and its canonically conjugate momentum, you set the these conditions. Now, I haven't said what F and F star are, and you can choose anything. And in particular, let's choose a solution. So what do the solutions look like? The solutions at very early times So very early times, eta is very, very large. And if we take any time derivative in the equation of motion of this eta, we get an eta cubed, for example, right? So that will be smaller compared to terms that contain only eta squared. So we can ignore the variation of eta for very early times. So for very early times, the equation will be just the equation of a harmonic oscillator. And the solutions will be similarly the solutions of a harmonic oscillator. So we'll have that f will be equal to e to the I k eta, okay? And with some prefactor that will vary slowly in eta for late times. So could be powers of eta and so on. Now, more explicitly for the case of free field, for a massless field, we have these particular solutions. Okay. And so we have these solutions. And as I said, these commutation relations will allow us to normalize these solutions. And you can more or less see how the normalization will work. So for very large eta, as I was mentioning, it was very similar to the harmonic oscillator. In fact, for very large eta, we get this factor of eta, which essentially cancels the factor of eta we have over there. And we have a harmonic oscillator. And then we should get the usual normalization of the harmonic oscillator, which is 1 over square root of omega, if you remember. And so we should get 1 over square root of k. But since there is this overall k here, we get here 1 over k to the 3/2. Again, you can, one of the exercises is to do this calculation. And I really recommend you do it with the 2's and everything, and the i's, so that you really understand how it's done. Okay, so these are the solutions, one particular basis of solutions. And now comes a very important issue, which is the choice of vacuum state or the choice of state that we should consider in the zeta space. And here we'll make a physical assumption. And notice that for very early times, when eta is very large, so let me mention the fact that so if we look at the causal past, this is Hubble volume at each time. This is the size or the coordinate size of the Hubble volume at each time. And if we are looking at mode with fixed k, as we are doing here, fixed k means fixed x distance, fixed comoving distance. These coordinates are sometimes called comoving coordinates. They are the coordinates of observers that just move together with in the FRW coordinates, and called for that reason comoving coordinates. And so for fixed x, the two observers which are at fixed x at very early times are within one Hubble horizon. And not only are they within one Hubble horizon, but they are occupying a fraction which is smaller and smaller in that Hubble horizon, right? So this distance is much smaller than this distance, which is, which is what? What is this proper distance? Yeah, r. Yeah, so this proper distance is r. This distance is much smaller than r. And so these two observers feel as if they are almost in flat space. Okay? And if we were doing this calculation in flat space, what would be? There would be some natural vacuum in flat space, which is the vacuum for the harmonic oscillator, these harmonic oscillators we have for each of the Fourier modes, right? So we could take the harmonic oscillator vacuum at early times, and that amounts to choosing a state 0, which is such that is annihilated by the by this annihilation operator. I mean, we had these commutation relations, but we haven't yet chosen the state. And we now made the choice of state by saying that at very early times, the state should look locally for an observer like the Minkowski vacuum. Okay. So that's an important choice of state, and we chose this particular state. Very good. And now that we've chosen this state, we can do some calculations, like, for example, calculating the expectation value of the field at some particular time. So again, we can do it in Fourier space. So equal time expectation values of the field. So that's roughly speaking taking the field. So we are doing it in Fourier space, but if we went back to position space, we would be, for example, considering the expectation values for the field at 2 points in time. Okay? Same instant in time, in global time, in this conformal time, and what we get is simply we just insert this expression for the field in here. Remember, these are classical solutions, and they are functions of eta. And so the field phi here in the left gets a contribution only from this term, because A annihilates the vacuum. And similarly, this one here on the left gets a contribution only from the second one. And so this is equal to modulus of f of eta squared. Okay? Okay, and now we can insert that expression here and the expression we had over there. And so for this is the expression we get for a massless field in Fourier space. Now, just as a check, let's see how this behaves for very early times. So what would you expect that the answer should be for very early times? So we said for very early times we should get the same results as in flat space, right? So let's check that we get the same result as in flat space, right? So what's the result in flat space for the 2-point correlation function at equal time? 1/k. Yeah, good. 1/k. And indeed, this is what we get from here up to these factors of eta, right? And the factors of eta really are necessary. Well, they are simply rescaling factors you would have if you are doing the change of coordinates and you were to express everything in proper coordinates, you would get these factors of eta. But certainly the k dependence is correct. Maybe you are used to the Fourier space propagator, which is 1/k0 squared. Sometimes it's written in usually Fourier transforms all four coordinates. But here what we are doing is we are going back to position space in time, or time. Well, yeah. We are Fourier transform the time component, and that's why we Fourier transform in k0, and that Fourier transform in k0 is what gives the 1/k. We look at the residue of the pole here, and we get the 1/k. Anyway, so that's the early time expression. And then for late times, we can neglect this. And so this is for eta. Well, there is an eta squared. For eta going to minus infinity. And then this goes like 1/k cubed for eta going to 0. Notice that at late times, this becomes time independent. So, and this is a feature for massless fields. If the field had a mass, then there would be some time dependence of this result. So, okay. And in the exercises, you can calculate, and you'll see what the time dependence is. Okay, very good. Now notice the point where you have a transition in behavior between the early times and the late times is when eta times k is of order 1. Now what is that special point? When is k times eta of order 1? So this is where we have a transition in behavior, where the field notices it's not in flat space anymore, and now it's in a different space, and you have different results. When is this? Yeah. So this is the point where we cross the horizon, right? So this distance here between these two observers is 1/k, right? And recall that well, if I had drawn this at really 45 degrees, this distance here, eta, would be equal to this distance eta here at horizon crossing. Okay. So that's what this condition is saying. Okay, very good. So that more or less explains the free field results. Yeah, we could go to position space, and in position space, this would look like phi of x. I'm going to only do the Fourier transform at late times. And if we do this Fourier transform, we would find something that goes like a log of x. But there's actually an infinity that comes from integrating the k cubed 1 over k cubed e to the ikx. And you can see that there is an infinity at small values of k. Okay, and that's this happens if you had a massless field in the zeta space. You definitely would get that the position space two-point function has this infrared infinity, and well, it's a feature. Now, in many other situations, such as in cosmology or slow roll inflation, this infinity is disposed of for physical reasons that will be explained, hopefully, in subsequent talks. Okay, now let's discuss this infinity. This infrared divergence is not present for massive fields. So for massive fields, we certainly don't have anything like this. Now let's discuss the introduction of interactions. So far we discussed the case of free fields, and we could choose this vacuum. This vacuum is sometimes called the adiabatic vacuum. It's also called the Euclidean vacuum because it comes from Euclidean continuation, as I'll explain in a second. It's also called Bunch-Davies vacuum. It's called Hartle-Hawking vacuum. It could also be called Chernikov-Tagirov vacuum, who were actually the first to talk about it. And anyway, so it has many names and so on. And the question is whether we can extend this vacuum to talk about interacting field theories. Is there anything wrong about interacting field theories in this vacuum? Okay, so we can consider, for example, a field or a massive field, and we can add a phi cube interaction. And let's see how we compute corrections to this result. So we can, for example, consider we can try to consider the expectation value of 3 field operators with, let's say, different momenta or the same momenta. I'm not going to describe the details of this calculation. I'm only going to describe some important points. So we're trying to compute this, so the expectation value of this 3-point function. Now, an important thing here is that we are computing an expectation value. We are not computing a transition amplitude. So this is, here we put some state, some 0, and what this 0 should be the vacuum of the interacting theory, which we should choose in some way. And that's what we are trying to compute. Now, in theories where we have time dependence, notice this vacuum. The way we're going to choose this vacuum is we're going to choose it by some past boundary conditions. So we're going to choose it by setting up some conditions that will be similar to this positive frequency condition for early times, right? Or this adiabatic vacuum at early times. So we're going to choose the vacuum at early times, and we choose both what appears here in the bra at early times and what appears here in the ket at early times. Okay. Good. Now this sounds too philosophical. So how does this translate in concrete calculation? Well, imagine you added a phi cubed interaction. Again, I'm talking about the lambda phi cubed, and we are trying to compute the correction to that correlator. So if you are very naive and you open the quantum field theory textbook in flat space that teaches you how to compute amplitudes, you would say, well, I just calculate this phi cubed. This is what I wanted to compute. Then I expand the Lagrangian. There is some coupling constant g here. Expand to first order. G phi cubed eta prime. And I integrate this between, well, minus infinity, the infinite past and the future. And we get this. Okay. Now this is the naive answer, and this is wrong. This gives you the wrong answer, and it's not even real in general. And we were computing expectation values of Hermitian operators. These are all evaluated at the same time. They commute, various phi's commute with each other, so it's really a Hermitian operator, and it better give us something real, but something like this would not. But yeah, so what's wrong with this? Well, what's wrong is that this is the prescription you see in quantum field theory books to compute transition amplitudes. In fact, the prescription you usually would see is something where you compute the time order expectation value of this kind. And this is also would be wrong to do this. So the correct thing to do is to take your initial state and evolve it up to, let's say, time eta. And so, well, I'm going to. So we apply the interaction Hamiltonian U, which involves an integral between minus infinity and eta, or plus infinity. And then we put the operator we want to compute. And then we have the same state here, take the adjoint of that state. And so we can read this formula saying we evolve from minus infinity to time eta, and then we evolve back to early times. So this can be expressed graphically as saying we have the time direction, we have time equal to 0, let's say, we have the time eta where we want to evaluate the object, and then we come and integrate here on the left, and then we integrate back to the right. Each of these integrals is a time order product of evolution operator e to the minus I interaction Hamiltonian, etc. And then this can be expressed as an anti-time ordered because we took the adjoint. And the whole thing together can be expressed as a correlation function of time order operators, where the operators are time ordered along this contour. So we have operators that are inserted here, which correspond to operators that come from the interaction Hamiltonians that came from this evolution operator. We also have operators inserted here that come from these guys. And in principle, we have to consider contractions between all these various fields that appear in these contours. And that's what will give us the full answer. OK? Now, can you see it already? No. This is tricky. OK. This is an easier solution. OK. Now, if you try to do this calculation in practice, you would see that, for example, there are contractions between. Let's consider the contribution for very early times. So there will be, let's say, 3 of these guys and 3 of these guys. There will be some contractions between this. And this contraction is nothing more than considering the time ordered across one of the 2 contours. Let's consider the upper one of field operators of this kind. So the same one that we considered here. So this is simply, so this contraction, what it means is that we are going to compute this expectation value in the unperturbed vacuum. Okay? And so we'll get from this term, we'll get an e to the I k eta prime, and from this, well, we'll get something else. But let's focus on this piece that depends on eta prime. This will be to the cubed, and there will be various powers of k here. What's important is that it's positive. So k, this is the modulus of k. This frequency is positive by the conditions we imposed on f, the adiabatic vacuum condition. And we should do this integral for early times. Okay, so this is an oscillatory integral, and we should decide what its value is, right? And so something we can do to give a meaning to this integral is to just move slightly the contour into the imaginary direction. So instead of integrating along the real contour as we were doing, so we give it a slight angle in the complex plane. So now this is imaginary parts of eta. This is real eta. And if we do that, then now eta gets replaced by eta plus I times some epsilon. Epsilon is this angle times the modulus of eta. And then you see that when we insert it here, we get something convergent. Okay? Now this is something you would do even if we are calculating the corrections to the ground state energy of a harmonic oscillator in flat space. So if you have a harmonic oscillator, you have an ordinary harmonic oscillator and you add a phi cubed interaction. I erased the Lagrangian we have over there, but just only the time direction. And you were computing the correction to the ground state energy, you would have to do something like this. Why? Because you have to choose the vacuum of the interacting theory. So if you just took just the free theory vacuum and you started doing this, these oscillations, what they physically mean is that you have a term where you are mixing the ground state with the state that contains 3 particles, right? And a mixture of these 3 will be the correct ground state, and a way to enforce the correct mixture is to do some evolution in imaginary time that projects onto the ground state. Okay? So we evolve in imaginary time over some time, and the evolution in imaginary time over a very long time, let's say if we had a time-independent Hamiltonian, it will project us onto the ground state, the state with lowest energy. Okay? Now this that we do in flat space is physically equivalent to this, and in fact we said that very early times we have something that looks very, very similar to flat space. Okay? So we are choosing the same prescription that we choose in flat space, exactly identical. Okay? Very good. Now that's for the plus contour, so the contour, the top contour here. Okay, we do that. We move it a little bit upwards, and for the down contour we do exactly the same, but we move it a little bit downwards because when we are looking at the second contour, this operator is on the left of this guy, and instead of having e to the IKT, we have e to the minus IKT. Okay, are you following? Or am I going too fast? Write bigger. Okay. I chose the big chalk, but it's. Okay. Let me see. Yes. Question.
It's propagating to the imaginary
yes.
axis. Is it simply because of getting over the singularity in your integration, or can you explain more?
No. Yeah. So the reason we have to go slightly into the imaginary direction is to choose a vacuum. This is the mathematical manifestation. This moving the contour is the mathematical language. I mean, I'm saying in mathematical language what in physical language would be to say that we choose the ordinary vacuum in flat space at very early times. Okay? So at very early times, we have this notion of being in a basically ordinary Minkowski vacuum. And that choice of Minkowski vacuum, so how do we do that choice in practice for an interacting theory? Well, we do this in perturbation theory. We do this evolution a little bit into imaginary time to project us onto the vacuum. That's what we always do in quantum field theory. I'm just trying to explain how to implement that in the Sitter space. Okay. Are there any other questions? Or? Okay. So now, and when you compute using this, you find for most, for all situations where you expect finite answers, you find finite answers. Well, this doesn't say too much, but for massive fields and interacting massive fields, this will lead to finite answers. When you have massless fields, there are subtleties because of these infrared divergences, and they, they are there. So, okay. Now, in some cases, those subtleties go away because of the physical observable you are computing. Okay, very good. So now let me So everything we said here seems to be closely tied to these coordinates, right? We went to very early times and so on. But what happens if we go to the global coordinates? So those global coordinates Lenny talked about. So these Poincare coordinates we are discussing cover these sections of the hyperboloid. Now, can we define the whole quantum field theory in interacting quantum field theory in the full de Sitter space? Notice here I'm just talking about quantum fields in de Sitter space. I'm not including dynamical gravity. So we're doing quantum field theory in de Sitter space. And I'm trying to move away from the free theory, which we think we understood, and then now we went to the interacting theory, and now we try to go back to the global coordinates and see what perspective this gives us. Okay, so far we've learned how to compute. So using these methods, we can compute correlation functions at any 2 points that are in this region of the hyperboloid. Okay. But using that, we can analytically continue those to any other region of the hyperboloid. Now, the first interesting fact is that when you analytically continue, there is no singularity here. So here there was no coordinate singularity. But these prescriptions that we were discussing here lead to no singularities in the correlators when you continue them past this region. This is not totally obvious. So you have to think a bit more about what this prescription means in order to realize that this will be the case. But you can continue them past this region. And in fact, they define 2-point functions or any correlation functions which are completely de Sitter invariant. They're invariant under the full isometries of de Sitter. Now, if you prove that this is de Sitter invariant, then it's guaranteed that it cannot have a singularity here, because the position of this is shifted around by de Sitter transformations. So what's slightly non-trivial is to show that, well, these things are fully de Sitter invariant. But anyway, so you get something completely de Sitter invariant, and that's something that you get can also be viewed in the following way. So Lenny talked about the sphere. So we have the S4. Now, we could consider a quantum field theory on S4. So we could take the massive field we were considering and considering it on S4 and add the interactions and consider now the interacting theory on S4. Now, if we do that, then we just use the usual rules of Euclidean quantum field theory, and we'll be able to do calculations in perturbation theory or even non-perturbatively on DS4 for that quantum field theory. Now, these two now the coordinates of this side of the Lorentzian, so we have hyperbolic Gauche, d omega 3. And the sphere is the same, but with, let's say, some angle phi and a cosine here of phi, right? And so we can, if we take tau to I phi, right, we get from this metric to that metric. And that corresponds to joining, okay. Now, in addition, if we take this quantum field theory on S4 and we take half of an S4, we could consider the functional integral over the fields of that theory with some boundary conditions for the field on this value, on this surface, on this S3. So we consider the full functional integral, and that will be, let me call that will be a wave functional for the values of the field, phi of x, or maybe I should call it phi of omega. So it depends on a function on a 3-sphere, right? So the function on a 3-sphere is the value of the field on this 3-sphere, and doing the full path integral will give us a number for each function. Okay, that's the full wave functional, and we can view this as the wave functional of the field at tau equal to 0 in the hyperboloid. Okay, and then we can evolve that wave functional with the interaction Hamiltonian everywhere in the rest of space, right? So that's a prescription for defining a vacuum of the theory in de Sitter. And that is a prescription which works for any interacting theory. And will give us a finite answer, a finite and de Sitter invariant answer for correlation functions in de Sitter space. Essentially, the de Sitter invariance is inherited from the spherical symmetry of the S4. So this wave functional realizes all the isometries of S4, and then this get analytically continued to the isometries of the Sitter space here. And so that is a procedure that works whenever the quantum field theory here is well defined. It will work. Now, I mentioned, by the way, I mentioned the fact that for a massless field, we had these infrared diversions, right? So a massless field is not something that is completely well defined in the Sitter space. So we cannot have simply a massless field. We cannot define the Sitter invariant two-point functions for a massless field. Now, what about on a sphere? Now, if we consider the massless field on a sphere, is it well defined?
If you define it.
What?
If you define it.
Well, I'm claiming that you cannot define it. Well, I'm just asking, if you compute the functional integral of the field on an S4, what's the problem, right? We have a massless field. We could just compute this. I could just compute this wave functional. I would get a wave functional. This is OK. But what will happen is that there is a zero mode, okay, of the field. And even though we can get a wave function of this kind, it will not be normalizable because of this zero mode. So it's just simply this trivial zero mode on S4 is that's the thing that is closely related or is intimately connected with this infrared diversions which we see here in full de Sitter. And this is actually something that extends even to interacting theories and so on. So it can happen that when you have massless or nearly massless fields, you have strong infrared effects and so on in de Sitter. And all of these things can eventually be computed by considering the sphere partition. I mean, going to Euclidean space and considering the sphere path integral. OK. Very good. So let me say one more thing about this choice of vacuum. Could I? Could? Yeah, if that mass is produced, then it's fine. Then it will be well. No, it's not enough. No, you should put whatever field theory you have. You have that full field theory with, if there is a mass, you include it. Yeah. Again, we are doing here quantum field theory. So in the Sitter space. Is the answer clear? So if you
yes, I would expect that.
Yeah.
It makes sense even if you think you start with zero mass, you start radiatively.
Right. Yeah, right. Yeah, then will be finite, and two-point functions in that theory will be well defined, and the Sitter invariant. Yeah. OK, so let me say one more thing about this contour issue. So let's draw this integration contour in the t-plane. So we have the tau plane of the Sitter here, these coordinates. Okay. So for very large tau, so we have that tau is basically like, e to the tau is minus 1 over eta. Well, this is the same formula that Lenny wrote. And so for very large tau, we'll have a contour very similar to that one. So we are doing some calculation here. We'll have to come here from somewhere and go back to somewhere. Okay. Now let's define that somewhere a little more precisely. So what we said is that it comes from analytically continuing this half sphere. Okay, so the half sphere here is along, so we have I pi over 2 here. So we are moving along imaginary time here. So when you try to define the Brouwer-Dequette, you are doing an integral along this contour. Okay. Now, this perturbation theory where you choose these contours that go forwards and backwards in time, these are sometimes called Keldysh contours, and this is just it's nothing mysterious about it. It's the way to calculate in quantum field theory or in quantum mechanics. It's the way to do perturbation theory when you know your initial state and you're trying to find how it evolves and so on. But this is the one we are choosing. And the correlation functions we find in this way are also analytic continuations of correlation functions on S4. So notice that if we were computing a similar expectation value where the points that we have, the point here we have is somewhere on S4, we would be doing, again, perturbation theory along the Euclidean S4. And what we are doing here is we are analytically continuing those correlators, and in doing so, all these perturbative contours follow the point and so on. So in fact, so as long as the field theory is defined on S4, it will then make sense also on the S4. Okay, now, very good. So now let me see what else. Do you have any further questions? Or?
Where did this contour arise from?
This contour, yeah. So. What? Yeah, this contour is, if you wish, the contour you should use when you do perturbation theory, and is the mathematical manifestation of the choice of vacuum. So we are choosing a vacuum, which is given by integrating over half of S4, and then continuing to Lorentzian signature DS space, right? And so that this integral over this Euclidean part of the S4 chooses the vacuum, and that corresponds to this part of the integral here, right? That's defining our vacuum. This corresponds to Lorentzian evolution in the zeta space, right? All this upper part is the computation of this at some late time, the vacuum state of the zeta space at some late time. Then we have some operators whose vevs we are trying to compute. That could be a product of various operators. They could also be inserted at various times. Okay? And then we go back. We have to put here the bra. The bra is the same kind of state as this one. So we have to do now the opposite. Go back in time, then choose the vacuum. So that's, yeah. With this prescription, if you went past here, the points where you're trying to evaluate, these two pieces of contour just cancel each other. Okay? So you only need really to go to the point where you're evaluating. That's simply the statement that nothing depends on the future. So if you're trying to evaluate something at time t, it doesn't matter what happens later. This is completely standard. This is what usually happens. It doesn't matter what happens later. The result you'll get for the expectation value will be independent of what happens in the future. Whether more or less particles were created and so on. Now, well, one remark that I think it's important is that this choice of vacuum really is choosing the vacuum for the quantum fields at somehow the middle here of the zeta space. This is different from what you would get if you somehow choose some vacuum here in the past and then propagate to the future. In fact, there isn't any really natural vacuum to choose here in the past, especially for interacting theories. So you could, for free theories, you might think there are some natural vacua here in the past. Like you could choose a vacuum which, for massive theory, for example, you could choose a vacuum that has no particles so that a local observer would see no particles. And you could then try to propagate this vacuum. But if you try to do then put in interactions, this infinite period of contractions will lead to divergences, physical divergences in the production rates of particles and so on. And so if you put a very small interaction, so you start from that vacuum that you might like, and you put some very small interaction, this period of contraction will lead to some singularity or some divergence. So really this vacuum that is chosen this way really has the boundary, is a vacuum that we choose at some intermediate time here. Okay? And this is a peculiarity. This is a feature of this vacuum. And indeed, there are problems in the zeta space if you try to choose the vacuum here in the past. You'll get some singularities and so on. And people have explored the singularities and exactly what happens when you do that. Okay, very good. Now, there is some. Is this the right vacuum to choose?
When you say there were singularities, you're imagining now gravitational vacuum.
No, even in interacting. I was mentioning interacting field theories. So let's say you add a phi cubed interaction, and then you will find some divergences in correlation functions, for example. So that, yeah, because you will have production of particles and so on, and these have been computed. And most recently, I think Polyakov and Krotov computed this, and they indeed find this feature.
You didn't mean singularities of the space-time.
No, not of the space-time. This I just meant we are here only doing quantum field theories in the zeta, and I'm trying to explain that the only vacuum that is known to give the zeta invariant answers and well-defined and so on is this vacuum that comes from S4. There are other vacua that people have defined, but those vacua have not yet been extended to interacting theories. And when you try to extend them, you get singularities of this kind. And they typically come from this issue of the contraction, if you try to choose some vacuum here in the past. This would have been the most naive thing to do. You have the space that contracts and expands. There is some past. You choose the vacuum in the past, and then you go into the future. I'm just pointing out this this feature. It's a feature of this vacuum that we are choosing. And this vacuum, so naively you would say, well, if you introduce a vacuum here in the middle, how can you extend it to interacting theories and so on? And the answer is yes, it can be extended to interacting theories. That's one of the main points I'm making here. Yeah. Yes.
You're going to get to the state at infinite past.
Yes.
Can you just say, you could start it off by saying that state is your vacuum?
Good. Yeah. So, yeah, you can certainly take whatever state you produce here by this analytic by continuing from the sphere and going back and say that this is your vacuum. But it is very hard to choose this state if you are someone living here. Okay. This is a vacuum that is highly complicated, very, very well. Let's do some philosophy here. So, what are we doing? So, imagine the case of the massless field. So we start from this vacuum of all these harmonic oscillators. We go to the future. How does the state look like in the future? Well, in the future, you have for each Fourier mode, you have some displacement. So the field is not at the minimum. So we discussed the harmonic oscillator. The field gets displaced from the minimum by some relatively big amount. Okay, where were we? Let me see. Well, we discussed that at late times, the mass goes to infinity, right? So if we had a harmonic oscillator with a mass going to infinity, we would expect it to be at the minimum, right? Exactly at the minimum. But it's not. We saw that the amplitude was some finite value of the field. It's really not at the minimum. And so we have this excited state, if you wish. And we have this universe full of waves of the scalar field. Okay, so for each Fourier mode, we have some wave. So, and it looks very complicated. So if someone at very late times look at this, the universe looks very complicated, like ours. It looks like ours. So our universe was supposedly created by a very simple state of a bunch of almost harmonic oscillators with small interactions, and it evolved into this. Now, if someone asks you, what state do you have to choose now so that if we evolve backwards, we get no singularity? Well, you will have to choose this and all possible superpositions that could have come from the Big Bang and inflation and so on, and it will be highly complicated. It would be very difficult to choose it. For us now, the most obvious state would be to put nothing, put no matter. That's the difficulty you face here. So if you put here a state with no particles, I discussed here the case of a massless field, but if we had done the massive field, then what we would find is that in each of the Hubble regions that Lenny discussed, so at very late times, in each Hubble region we would have some massive particle with probability e to the minus m over h. Okay? In each Hubble patch, this is the probability of finding a massive particle in each Hubble patch. Right? That's the state that is produced by inflation. And if we if we set this to 0, we said, well, we have no we look at the state that has no massive particle in any of these Hubble patches. That defines the state. We could define the state either in the past or the future. And then if we evolve that state, we have that problem. Now, let me say this more clearly here. So we cut this off at some very early time, and we find a lot of Hubble patches. We say we have no particle in any of the Hubble patches. We evolve into the future. If it's an interacting theory, you'll get problems. You'll get singularities and things like that. So, okay. And the basic reason can be understood from the static patch picture. I mean, you're in the static patch, this state that we were discussing is a state that is in thermal equilibrium. And the way to see that is what Lenny already discussed, the fact that you can do another analytic continuation of this S4 that directly gives you the static patch. So, and that shows quite clearly that the static patch are correlators of a thermal field theory. And so, I mean, these changes of coordinates are very powerful. They allow you to make statements about arbitrary interacting field theories and so on. And now, if you start with a state that is not the thermal state, then you will have singularities. You might have singularities here on the horizon. You might have, or you might want to go back to the thermal state. Those are things that could happen. And these are the types of things that lead to singularities. The details of what happens in each case depends on each situation you choose. Okay. Any other question? Okay, so now I would like to, in order to continue this idea of understanding this calculation from different points of view, let's try to understand this calculation from the wave function point of view. So here we discussed the fact that we calculate this wave function at this time, and then we calculate it at late times by evolving. So what is that wave function exactly? Now, if we're given the 2-point function for a Gaussian field, then we can compute its wave function. Well, more precisely, we would be able to compute directly the square of the wave function. So we discussed this, at least at late times, went like 1 over k cubed, for example. And then if we were to calculate, that means that the square of the wave function at late times should go like what? So what Gaussian gives us, so it should be a Gaussian, so it should be something that goes like phi squared with some coefficient here in front such that when we compute expectation values, we get 1 over k cubed. And well, should be k cubed, right? So that if this is very large, the field will want to be very close phi equal to 0. And so if k cubed is very large, this is very small, and indeed phi squared will be very close to 0. Now, okay, so we get this wave functional, and in principle we could even write it down as a function of x and x prime and so on. So if we want to insist on that, so we would get that this is something that looks I'm really Fourier transform this back to position space. So this is just the Fourier transform of this distribution to position space. It's only going to be a function of x minus y, and whatever appears here is just the Fourier transform of k cubed. So we have d cubed k, k cubed e to the I k, let's say x minus y. And so this has dimensions in k which are 6, so we have 3 from here and 3 from here. So by dimensional analysis, it should go like x minus y to the 6th power. It's divergent for very large k, so it has some divergences. But the divergence, so very large k corresponds to very short distances in position space. So the wave function is like this for long enough distances, and then it will have some other terms, and discuss them in more detail later, that involve squares of phi at the same position, with possibly divergent coefficients, or maybe derivatives of phi at the same position. Okay? So the point here is that the non-local part of the wave function is determined by this piece, which is not analytic in k, and there could be some other pieces which are analytic in k that determine these other parts of the wave function. Okay. Okay, very good. Now, let me discuss a little more the gravitational case. Well, maybe I would mention one more thing, right? Is it clear how we go from the two-point function to the wave function? It's a simple thing, right? Yes?
You've used the fact that the wave function is real.
Well, I wrote for the square of the wave function that this is. I'm not saying what the wave function, what the phase of the wave function is yet.
But you know that it's real.
No, it's actually not real. But it's actually not real.
Oh, this is a late time.
This is a late time. Yeah, exactly. Yeah. Oh, yeah, that's important. Yeah, I'm computing the wave function at late times. This is not the very important point. This is not the wave function at here on the equator of the sphere. This is taking that wave function, which is how we define the original state, and evolving it to very late times, and then taking a very late time cross section and looking at the wave function for long distance fluctuations. The fluctuations here of phi, the x dependence of phi is very slow. It's over many, many Hubble volumes. So we're taking a phi which has this shape, and then we're considering a late time cutoff which includes many, many Hubble volumes. So the universe looks very uniform on that scale. Okay. So describing the wave functional or wave function of the universe, or describing the two-point function, is basically the same. We lose some information in going from the wave function to the two-point function, and we could recover some information about this phase if we computed those two-point functions at different times.
What is the significance of that non-local term?
Yeah. So this non-local term takes into account the non-local correlations between different regions, the phi in different regions of the sky, of the different points in the zeta space that are out of causal contact. They are in different Hubble volumes, and we're considering the correlation, we're considering the probability that we see one phi here and another phi here. Okay. I mean, when we say that when we say that the fluctuations in the CMB are Gaussian, we're saying that the wave function probability distribution is Gaussian. It's a Gaussian like this. Okay. That's what we're saying. Now, the reason I'm talking about this wave function is because when we do calculations in ADS, what we very naturally compute is an object very similar to this wave function. And that's why I'm mentioning the wave function right now. Okay. Let me discuss a few features of the gravity calculation. So now we're going to leave the quantum field theory story to go to the gravity calculation. So we'll have the action of Einstein gravity with its usual action. I'm going to rewrite lambda in terms of some radius of ADS, radius of ds, which is just defined through the equation that Lenny mentioned this morning. So I'm going to just write the action as m squared over h squared. H squared is just a constant. It's just a redefinition of what lambda means. And I'm going to write it like -2 or -6. So it depends on how you like to define things. So if we define it this way, then the radius of a solution of this equation, of this action, will be the sitter with radius set to 1. Okay. Very good. So we have this action. And we can compute, let's try to repeat the calculation of fluctuations that we discussed over there. So the calculation of fluctuations is very similar. The graviton, it's almost identical to what we discussed earlier. There is some issue of choosing a particular gauge. So we choose some gauge for the graviton. So we can write the metric in this way, where we set to 0 various components of the metric, the time components and the 0 and I components. And then we can think of this as dynamical variables. So to quadratic order, we have only the transverse traceless parts of H. And they obey an equation which is identical to the equation of massless fields that we discussed earlier. So we have exactly the same as what we had there, with only one small difference, which is that there is this overall factor here in the action. And the result, therefore, will be the same as what we got before, except that now the field H will have a 2-point function, which will contain this fact. I mean, that this overall factor in front of the action translates into a new overall factor in front of the 2-point correlator. Okay, will be of this form in Fourier space. Okay, so again, the typical fluctuations of the graviton are of the order of h squared over m Planck squared. So the bigger, the smaller h is, so the less rapidly that the universe is expanding, the smaller the fluctuations for the graviton will be. Okay, so notice that h has a natural normalization. In these coordinates, it would be dimensionless. So it's telling you how big the deviation from the flat slices you will have in the future. Okay. Yeah, since the gravity case is almost identical to the scalar field case. Oh, one more thing I need to mention about that. So we saw that there was some infrared divergence for a scalar field. Now you can worry about that for the case of gravity. Now gravity, so if we go back to the S4 calculation, gravity on S4 seems to be perfectly fine. There are no 0 modes for the graviton on S4. So you can calculate the equations of motion. There is no 0 mode solution. And so, in fact, this divergence that we see here can be attributed to a gauge mode. So it's due to some gauge mode, and if you compute more gauge invariant observables, you will not have this divergence. Or you could choose to express the graviton correlator in some other gauge, and it will not have this the infrared divergence. Okay. Yes.
Physical terms, if I were to measure this 2-point function,
Yeah.
from experiment,
Yeah.
very small, to measure it now in our universe,
Yeah.
h squared,
Yeah.
what would I measure?
Yeah, so no, you cannot measure in our universe this h. These 2-point functions are always for super horizon fluctuations. In order to measure it in our universe, you would need first that we'll enter a period of slow roll inflation, and our universe will inflate for quite a while, and then it will produce a new universe with smaller cosmological constant, and those observers in that new universe would be able to measure that. This is not something that we can. So if we here set h to be the Hubble radius today, we are not going to be measuring this. We cannot measure this. Okay.
Because it's a gauge mode, or because
No. It's no. Even for the scalar field, I mean, here this.
if
there are two different issues. So one, yeah, I think I confused the issues here. Let's consider the case of a scalar field. Okay, no gauge modes there, and you can ask whether you can measure this two-point function for super horizon fluctuations, and the answer is no, because in order to measure this, what you need is you need to calculate the value of the field here and here, right, and see how correlated they are, right? And you need to do it at times which are bigger than the horizon size at this time, right? So this distance has to be much bigger than the horizon size, which is this little piece here. Okay. So it really involves something. This guy cannot send you a signal of how big your the phi was in here, right? So directly cannot be measured. So we are, when we talk about this, yes, maybe you should emphasize this point. This is an important point. So when we talk about these observables, computing these two-point functions at late times, and we take this late time limit, for example, where the correlation functions became time independent, we are talking about things that no observer who lives in this de Sitter can measure. Okay? It is something you can calculate, but not necessarily something that an observer that lives in the space can measure. Okay? It is interesting that if we look at the very early universe, right, at the period, at the inflating universe, it looked like this for a while, and then there was the end of inflation, right? And then it continued for a while, and now we are here, and we can actually see these two guys. Okay, we can see the values of the field here, and we can compute it. So we are now we can now measure these observables for the early universe, right? So the only way, well, one way to measure the observables for the current universe is if it undergoes a similar period of inflation and so on. But just from the point of view of pure de Sitter, is something you can calculate, but not something that anybody living in the space can measure. Okay, something. Okay. Anyway. Yeah. Is that?
The same story goes through for graviton. So
the same goes through. The same goes through for graviton. All I was talking about here when I talked about infrared divergences is the k equal to 0 mode, just k equal to 0. The fact that this diverges for k equal to 0, there is a problem, and that problem is not really there. But it's only for that mode. All the rest of the modes, finite k is perfectly well defined, and but it cannot be measured by an observer who lives in the space. Okay, the observers who live in the space can measure things at distances shorter than the horizon. Now, maybe they could extract some information about these guys by looking at things that are very close to the horizon and so on. So it would be a more subtle way of measuring those things, but, well, it's a little less clear. But if you just really try to measure these observables, they cannot be measured by an observer who lives in one of these spaces. Yeah.
This power law, nice power law
Yeah.
expressions.
Yes. Yes.
Presumably there's a crossover at small enough distance where they cross over to something else. And that crossover
Exactly,
must
yeah.
be at the horizon.
Yeah, exactly, yes. Absolutely, yeah.
Right. And I'm pointing that out because
Yes.
it's connected with what I said this morning.
Yes.
That the horizon size sort of provides a lattice cell for
Yes,
the
yes, yes.
cell size.
Yes, yes, exactly, yeah, yeah. Yeah, so these things with the nice power law or the time independence, recall that when we were calculating these quantities, we had a 1 plus k squared beta squared, right? And this is, again, the same effect. I mean, when we're looking at distances or values of k which are comparable to eta, we're crossing over from the long distance size to the short distances within the horizon. Okay. Now, let me okay, I'll start the calculation. I'm not sure if I have enough time to finish it. For how to of calculating this wave function directly. So what we're doing is we have the Sitter space, and the two-point function is a calculation of, let's say, some Feynman diagram like this. And
Wow, a little bit darker.
yeah. So we're calculating some Feynman diagrams like this. And the calculation of Feynman diagrams is intimately connected to finding solutions of the equations of motion. So if you calculate 3-level Feynman diagrams, so for example, we could even compute 3-point functions and so on, and evaluate the wave function of the universe that computes all these 3-level diagrams. That is contained in a solution of the classical equations of motion. So that's a general feature about quantum field theory. So if you have in quantum field theory, you are evaluating some Feynman diagram, that Feynman diagram can be extracted from a solution of the classical equations. And all you need to understand is which solution of the classical equations you should consider. Well, I should say it something more. So you are considering some solution of some classical solution, and you are evaluating the action on the classical solution. So that's what will evaluate Feynman diagrams for you. Well, these 3-level Feynman diagrams for you. And all you need to understand is which classical solutions you should consider. Okay. So now let's consider the situation we are considering here, where we are setting some boundary conditions in the future, and we are looking at the wave function as a function of those boundary conditions. Let's call it phi b. Okay, there is some phi b here. This is the value of the field at very late times or at some cutoff time. Doesn't matter too much. So we are trying to evaluate that wave function, and so it's natural to think that we'll choose a phi such that at that late time, so let's say eta equal to 0, phi will be phi b of x. Okay, so this is a function of x and eta. This is a function of x and eta. We evaluate it at late times at eta equal to 0. It will be some function phi b of x. Very good. Now, that's one boundary condition that doesn't specify the classical solution completely. We should specify it by choosing some boundary conditions in the past. Okay? So which boundary conditions in the past should we choose? Well, recall that when we were looking at that problem, at the problem of the free scalar field, we chose particular solutions that had this positive frequency boundary condition in the past. So in the past, they looked like e to the I k eta. Okay. And indeed, this is the right type of boundary condition to impose on these classical solutions if what we are doing is calculating this wave function. And one way to see that is that imagine we are calculating this wave function of phi, right? And now so that's the answer of some calculation where we impose some boundary condition in the future, and we are trying to figure out what the boundary condition in the past is. But now let me consider a slightly different problem where we add a field at some position x. Okay? So if we add some field at some position x, what we are doing is at this classical level, we would find the expectation value of that by evaluating the classical solution on this field. Okay? But that has the interpretation of coming, let's say, from the Bunch-Davies vacuum and acting with. Okay, let me. So the wave function as a function of phi can be written as phi b of x. So this is a kind of position basis for the field, and then we have the Bunch-Davies vacuum or Hartley-Hawking vacuum, right? That's by definition what the wave function is. So for harmonic oscillator, similar notation would be x0. That would be e to the minus x squared. So the wave function of the harmonic oscillator. So we have the vacuum, and then we evaluate in position basis. We get the function of the position. We have the Bunch-Davies vacuum. We evaluate as a function of phi of x. We get some functional of phi of x. Okay? So that's the calculation of the wave function. And now we could do the same calculation, but insert some field at some early time. But this field acting on the vacuum will will contain that, will be of that form. And the only piece that will contribute will be the piece involving f, the function f, that if you, unfortunately, I erased it, that was the one that behaved like positive frequencies at early times. Okay. Anyway, so that's what we should get if we evaluate this. If we put in this value of the field phi here, but in the semi-classical approximation, this answer, the value, so phi b of x to leading order is given by replacing this by phi b of x and eta, okay, the full classical solution, whatever it is. And so what this is saying is that the full classical solution, whatever it is, better behave like this at early times. This is simply just deriving for you why we should consider classical solutions that behave like this when eta goes to minus infinity, that is early times. Okay? Is that clear? Yeah.
Sorry, I don't understand what's phi b on the left.
Phi b? Yeah, so we are evaluating the wave functional of some function phi b of x. Yeah, I think it was my fault. Not. Is it now more clear? Yeah. Yeah, so phi b appears in the calculation because that's the profile we set for the field at the future. So what we are doing is we are trying to calculate the probability that we detect some value phi b of x at late times. Okay, that's what we are trying to calculate, or at some time. I mean, here it doesn't matter whether we are late times or early times. The answer is, I mean, what we would do is the same. I mean, the final answer will be different in the two. But we could do this for any time. We have some phi b of x at any time, and then we evaluate the overlap with the vacuum, and that would give us the probability of finding that particular shape for the field. Okay. Yeah, phi b is real. Phi is not real. Yeah, maybe I should emphasize that. What? No. You definitely cannot make phi real all the time because the condition is that it contains only positive frequencies. So if you wanted a phi which is real, then it should also contain the negative frequencies. Phi is not real. It is crucial that phi is not real. And why is it crucial? Well, when we evaluate the wave function, we are going to evaluate I times the classical action on that classical solution, which is a function of x and eta, right? Now, if this phi was real, then this wave function would be a pure phase, and we would square it. It would be completely independent of the profile. Okay? So it's crucial that it's not real, so that we get something that actually depends on the profile for the square of the wave function or the probability of seeing various shapes for the scalar field. Okay. Okay, now, okay, so this is what we would like to calculate. And so let's try to calculate this. So we have, so what are the rules? We should find a solution of the classical equations with this boundary condition and so on. So let's do this for each Fourier mode. Okay. So we'll have, we'll look for a solution of the classical equations. The solutions of the classical equations are functions for each Fourier mode that go like e to the minus ik eta, e to the ik eta. So this is a solution which obeys the right boundary conditions in the far future, okay? In the far past for very negative eta. And now we should obey also the correct boundary conditions at late times. And late times is some phi b. So it's some phi b of k. Okay. So this is the data that the wave function will depend on, and this is the full solution as a function of eta. Okay. So that's what we would like to evaluate, and so we can take this and now take the classical action, and we can insert this in the classical action. Now here there is some little trick which involves integrating this by parts. So there is a term of the form where we take the gradient acting on the other field, but since we're evaluating in a classical solution, this will be 0. And so this whole thing will be just simply a boundary term of the form 1 over eta squared phi d eta phi. Okay? And all this evaluated at eta equal to 0. Okay? Very good. So, and now what we need to do is, well, this already becomes phi b, which we're evaluating at eta equal to 0. And now we should take this derivative of this function. And, okay, so what will be the derivative? So there are a bunch of terms. So there is a term that where we take the derivative of this times that, and that gives us a k square eta e to the I k eta, right? So a term like that. And I think the other terms cancel, but you can check it. And when we multiply by 1 over eta, so you get in total a 1 over eta, and we should evaluate this at eta equal to 0. And we see that we see that we get infinity, right? We get infinity from this factor. Okay. So let's regulate and say we evaluate it at some eta c, which is some cutoff eta, or let me call it epsilon, some epsilon. There is a term 1 over epsilon k squared. And then there is another term that comes from expanding this to first order that is of the form I k cubed. And this has no epsilon now. This piece is finite, right? So we're evaluating the exponential to first order, and we get this term. Okay. Okay, very good. Now this was the value of the classical action. We go back to this formula, and we put it back in here. So we get e to the I. We get the 1 over epsilon phi b of k squared times k squared, right? So that came from this term. And then we get the factor from that term, and the two i's cancel, and we get e to the minus phi b squared k cubed. Okay? Now, if we were to take the modulus of this wave function, then this divergence would, this term that is a phase, this diversion term would cancel, and we'll only get this factor, which had the form we expected. So let me, I erased it, sorry. So this had the form of the Gaussian wave function. We expected for a scalar field that would reproduce the usual result. Okay, so yeah, I think I'll probably have to end here. This I should mention this factor, this divergent factor, it's the one that is given the evolution of the field within the horizon. So it's a phase and so on. So it affects, let's say, the momentum, the conjugate momentum. It gives us some time derivative for the field, and it's giving us the evolution of the field inside the horizon. And so the super horizon fluctuations, which are these ones here, do not well. First of all, they do not depend on time, and they are constant, and they don't have these diversions. Okay, I'll end here, and next time we'll discuss more the similarities of this type of calculations with similar calculations in ideal space. Thank you.